screen is visible, right, sir? Can you confirm?
Yes, let's start.
Yeah. Okay. So very good evening, everyone. Welcome you all to IGC. So today we are here with a session on previous year solutions of GATE 2009 Aerospace Engineering paper. So in this paper, we'll be discussing solutions of the questions related to aerodynamics. Okay. So if you see the type of questions that were asked in aerodynamics, the number of questions, there were 3 questions of 1 mark. There were 4 questions of 2 marks. So in total, there were around 11 questions, right? So this is the number. Typically in every year, you can expect questions from aerodynamics to be around 10 to 15. Okay, so around 10 to 15 questions in aerodynamics can be expected. And if you see the type of questions that have been asked in this particular year, that is 2009, okay, all the questions were very easy. Okay, so if you are strong in your basics, you can crack it in no time. Okay, they were literally easy, except for one question which was kind of moderate. Okay, so let's now look into the questions and let's solve them one by one. So let's start. Okay, so this is the first question. This was question number 2 in that paper. So this is a 1 marker question, right? So what does this question say? This question says that for 2-dimensional irrotational and incompressible flows, right? So the keywords here are irrotational and incompressible flows. Now let's look at the options, right? So they are asking for this category of flows, which of the options are true? So the options say that option A is that both potential and stream functions satisfy the Laplace equation. So you see these words: potential function, stream function, Laplace equation. Okay. And you see the other options. So all the options are basically asking whether which of these two, potential function or stream function, they satisfy the Laplace equation, right? That is the question over here. So right, so let's now start figuring it out how to solve. So when you read this question, what should come to your mind? What should strike you first? That you see these words, right? Potential function and stream function. So the moment you see this, you should go back to your basics of fluid kinematics, right? So in fluid kinematics, you would have defined these functions like potential function, right? Potential function is basically defined by, denoted by phi, right? So this is the potential function. So now you would basically recollect where you would have learned this potential function, right? So it is in fluid kinematics. So please recall where this potential function is defined. Where was this originated from, right? So the basic assumption involved in defining this potential function was that the flow is irrotational, right? The flow is irrotational. So we define this potential function for an irrotational flow. Right? Now, what is so special about this irrotational flow, right? You all would have learned irrotational flows in great detail. So let's mathematically represent this irrotational flow. So you know that for any flow to be irrotational, it should satisfy the condition of vorticity vector going to 0, right? So vorticity goes to 0 for an irrotational flow. Now, what is this vorticity? Vorticity is mathematically nothing but curl of velocity vector that goes to 0. All right. So if this condition is satisfied, okay, that the curl of velocity vector when it goes to 0, you can say that the flow is irrotational. Okay. Now, when you define such a condition, from this condition, you can always say that from vector calculus, from the identities of vector calculus, you can always represent this velocity vector to be a gradient of a scalar potential function like phi. Okay, So phi is a scalar potential function. The gradient of this phi can be represented by this velocity vector, right? So because you can define such a potential, such a function, scalar function like this phi, these flows are called as potential flows, right? So this potential function at the first place comes into picture only for the potential flows or irrotational flows. Okay, so you can define v is equal to gradient of phi, right? So let's call this as equation 1, right? Now you go back to the question. What question says? The question says that the flow is not just irrotational, but it is also incompressible, right? So now let's invoke the incompressibility criterion. Right. So what is the incompressibility condition? The incompressibility condition is that, what is the incompressibility condition, guys? It is that del dot v is equal to 0, right? The divergence of velocity goes to 0. This is the incompressibility condition. And this is also known as what? This is also known as continuity equation. Okay. This is also known as continuity equation for incompressible flows. Remember, this form is only valid for incompressible flows. When you deal with compressible flows, you will also have terms related to rho, right? Density will come into picture, right? So this is for incompressibility condition. So let's say this is equation number 2. Okay. Now let's say we combine equation 1 and 2. What do we get? So equation 2 says that del dot v is equal to 0, right? Now instead of v, I'm substituting equation 1. So it is del dot del phi is equal to 0. So this means del square phi is equal to 0, right? What is this? What is this equation, guys? Can you recall this equation? Del square phi is equal to 0. Have you come across this anywhere in fluid dynamics? Yeah. So this is nothing but the Laplace equation. Okay. This is the Laplace equation. Okay. So now you can see that when the flow is irrotational and the flow is incompressible, phi, that is the velocity potential function, satisfies the Laplace equation. Okay. So you can also represent this in two-dimensional form, right? How do you represent this in two-dimensional form? Del square phi by del x square plus del square phi by del y square is equal to 0, right? This is how you, this is square. Okay, this is how you represent this in two-dimensional form, right? So any equation of this type is known as Laplace equation, but here we can clearly see that phi satisfies Laplace equation. Okay, now let's consider psi. Okay, let's consider psi. So what is psi? Psi is the stream function. Psi is the stream function. So again, go back to your fluid kinematics. Recall, where did you define psi? So psi was defined for an, psi is defined for a 2D, two-dimensional incompressible flow. Okay, psi is defined for a two-dimensional incompressible flow. So psi comes from the incompressibility condition. So what is the incompressibility condition, as we had already seen in the previous discussion? That is del dot v is equal to 0. Okay, so del dot v is equal to 0 is the incompressibility condition. So how can you write down this in two-dimensional form? Dou u by dou x plus dou v by dou y is equal to 0, right? So from here, if you want to represent this velocity components u and v, okay, in terms of the stream function, then you can write down u is equal to dou psi by dou y and v is equal to minus dou psi by dou x. Okay, So this is how you define psi. So the definition of psi comes from the incompressibility condition. Okay. So now let's say psi also satisfies irrotationality condition. Okay. Let's say psi also satisfies the irrotationality condition. So what is the irrotationality condition for 2D? Okay. What is the irrotationality condition for 2D? Again, it is the same, right? Del cross V is equal to 0. But when you write this in 2D, it becomes dou V by dou Y minus dou U by dou X is equal to 0, right? Now you substitute these velocity components U and V using the definition of psi from here. Let's say this is equation 3. So from equation 3, you can substitute U and V, right? So what do you get? You will get minus, sorry, this is dou V by dou X, right? So please correct this. This is dou V by dou X and this is dou U by dou Y, okay? So if you substitute this, what do you get? Del square psi by del X square minus del square psi by del Y square is equal to 0. So from here also you can see that clearly del square psi is equal to 0. So again, you can observe that psi, the stream function, also satisfies the Laplace equation. Okay. Okay. Psi also satisfies the Laplace equation. So we have thus seen both phi and psi satisfy the Laplace equation. So which option is correct, guys? Out of this, which option is correct? Option A, right? Both phi and psi satisfy the Laplace equation, right? So this is the this Laplace equation is the most fundamental tool of potential flows. All the elementary potential flows can be superimposed to form new combination of flows by using this Laplace equation. So it is a second order linear PDE, but although it is a very powerful tool in potential flows. Okay. So I hope this question is clear to you all. So shall we move on to the next question? All right. So we'll move on to the next question. Right. So this is question number 3 in 2009 paper. Again, this was for 1 mark. Okay. So let's see what this question says. A trailing edge plane flap deflected downward increases the lift coefficient of an airfoil by what? Right. So they are saying that you have an aerofoil. Okay. You have an aerofoil and you have a trailing edge flap. Okay. So basically it's a trailing edge flap. It is deflected downwards. So this is delta. Okay. It is deflected downwards. And when it is deflected downwards, it increases the lift coefficient. Okay. So it increases the CL for this aerofoil by what? So what is the mechanism by which the lift can be increased by deploying this flap, right? So let's try to understand what is the mechanism. Okay. So you consider an aerofoil. Okay, let's consider it as an aerofoil. So say this is a positively cambered aerofoil, right? So when it is a positively cambered aerofoil, we can always draw a mean camber line. Okay, this is the camber line. Okay, you can draw a mean camber line. And so basically when you draw the lift curve slope, lift curve for this aerofoil, that is CL versus alpha curve, how does it look like? It will look like something like this, right? So this aerofoil is going to have a zero lift angle of attack called as alpha L is equal to 0, right? And it is going to have a lift curve slope, which is generally 2 pi as predicted by the thin aerofoil theory, right? But here in this question, they do not say anything about the lift curve slope. So maybe you can assume it to be 2 pi, okay? Yeah, all right. So this is a lift curve slope for this general aerofoil, which is say positively cambered. Now, if I add a flap, okay, if I have a flap and say this flap is deflected downwards, okay, so the downward deflection of flap is by convention always positive, right? By convention, it is always positive. So, so what does what happens here? So basically, what is a flap? So flap is nothing but a high lift device. Flap is a high lift device. So what are the high lift devices that you know? One is flap, another is slat, right? Flaps and slats. So these are the like most commonly deployed high lift devices in an aircraft, right? So where is flaps found? Flaps are usually found at the trailing edge. So at the trailing edge, you have a segment which is hinged to the trailing edge of the aerofoil, and it can move up or down, right? So in this case, this particular flap is deflected downwards. Now, why do we call them as high lift devices? Because they increase the lift of the aerofoil, right? So this is in the normal case, this is the lift curve. But when you deploy these flaps and slats, the lift coefficient increases, right? For a given angle of attack, you can observe that the lift coefficient increases. Now they are asking what is the mechanism through which this lift coefficient is increased, right? So for that, let's just look at the lift equation, right? So what is the lift equation for a positively cambered airfoil? You can write CL is equal to lift curve slope, which is A. So here, in this case, we do not know whether thin airfoil theory is applicable. So let's just call the lift curve slope as A. Okay. So CL is equal to A into alpha minus alpha L is equal to 0. So you also have the zero lift angle of attack, right? All right. So this is the lift equation. Now, how can CL be increased, right? How can CL be increased at a given angle of attack? Okay, at a given angle of attack. So you can see that when you deploy the flap, your lift curve is generally going to shift towards left, right? Is generally going to shift towards left. Okay? But you will observe that the lift curve slope remains the same. Lift curve slope remains the same. Only thing is that your lift curve is going to shift towards left. Okay. So so now A is fixed, right? And say we are looking at a given angle of attack alpha. So say I'm looking at this particular alpha. Okay. So you can say this particular alpha, the lift without flap and the lift with flap. Okay. So this is with flap and this is without flap. Okay. So alpha is fixed. So alpha L is equal to 0 is an additional parameter in this lift, which can help me to alter the lift, right? So how can I increase my CL? Should I increase my alpha L is equal to 0 or should I decrease it? You know, for a positively cambered airfoil, okay? For a positively cambered airfoil, usually alpha L is equal to 0 is negative. Okay, so because this is negative, the complete lift becomes positive. Okay, so if you modify this alpha L is equal to 0, zero lift angle of attack, or basically if I make it more negative, okay, if we make it more negative, then I can achieve an increase in lift. That is what you can observe from the lift curve that I have drawn here, right? You can see that the alpha L is equal to 0 becomes more negative, right? When you shift the lift curve. So what does this physically mean now? So when I change alpha L is equal to 0, indirectly what I am changing is the camber of the aerofoil. Camber of the aerofoil. So the camber of the aerofoil is being changed when we change alpha L is equal to 0, right? So it is not just the camber, it's the effective camber that is changed, because already this aerofoil has some camber, some positive camber. When you deploy the flap, you can see that this shape has now changed, right? So the camber line equation has now changed. That is the reason alpha L is equal to 0 is changed. Okay. If you want to show this mathematically also, you can show from thin airfoil theory. Okay. From thin aerofoil theory, we know that alpha L is equal to 0 is given by 1 by pi from 0 to pi dy by dx into 1 minus cos theta d theta. Correct? This is how alpha L is equal to 0 is given. You can see that alpha L is equal to 0 directly depends upon dy by dx, which is nothing but the slope of camber line. Slope of camber line. Okay. So when you change the camber line, you are basically changing your alpha L is equal to 0. So in this case, when you deflect the flap downwards, your alpha L is equal to 0, that is the zero lift angle of attack, becomes more negative. Thereby, you achieve a higher lift coefficient. So basically what you are doing, you are changing the effective camber. Now let's go back to the question and look at the options. So what do you see here? Let's option A says that increasing the effective camber of the airfoil. This is what we had reasoned out, right? So this should be a valid correct option. But let's also see other options, right? Let's understand them, why they are wrong. So option B says delaying the separation of flow from the airfoil surface. So separation of flow. See, separation of flow is basically it is not an inviscid phenomena, right? It is due to viscous effects, right? When you keep the airfoil at high angle of attack, the flow separates from the leading edge or from the trailing edge. So it is basically a viscous phenomena. So this viscous phenomena is usually not modeled by thin airfoil theory. Okay, it is not modeled by thin airfoil theory. Thin airfoil theory is only valid up to the linear regime of this lift curve. So only when this lift curve is straight, thin airfoil theory equations and principles are valid. Okay, not when the flow has been separated. Okay, so you cannot say when the flow has separated, you cannot basically comment on the lift coefficient when the flow is separated. Okay, so basically where does flow separate? Flow separates at stall, right? You can see the stall. This is alpha stall. You can see at stall angle of attack, the lift suddenly drops down. So this is all when the viscous effect starts to kick in. Okay, so you cannot say due to the flow separation. This is wrong. Now let's look at option C. Option C says that increasing the local airspeed near the trailing edge. Right now you don't know what type of airfoil it is. If the airfoil is a finite angle trailing edge airfoil, then the trailing edge is going to be a stagnation point, right? So basically the speed near the trailing edge is taken care by Kutta condition, right? So that does not play, or that is not very clear as to how this will contribute to CL. Okay. And option D says that controlling the growth of boundary layer thickness along the airfoil surface. So boundary layer is always, there is obviously going to be some boundary layer over the airfoil surface, but this boundary layer is, the shape of the boundary layer is more determined by the geometry of the aerofoil. Now the boundary layer is going to start from the leading edge, right? And most probably towards the trailing edge is where it boundary layer is going to separate, right? So the flap is at the trailing edge, right? So at the leading edge, still boundary layer growth is not controlled. So definitely growth of boundary layer is not a reason for increase in CL, right? So even if you deflect the flap or you do not deflect the flap, boundary layer is still going to be there and that is going to cause some drag, right? So even option D is not a correct explanation. Okay, so we have seen all the options, right? So option A is the most suitable. I hope this question is clear to you all. Okay. So shall we move to the next question? All right. So the next question is also much similar to the one that we have discussed already. This is again a one marker question. Okay. This question says that thin airfoil theory predicts that lift curve slope is dCl by d alpha, which is equal to 2 pi for what type of airfoils, right? So what do you think the answer would be? Guys, if you are watching the session, can you please comment what do you think the answer should be for this question? Yeah, all right. So yeah, so let's, okay, someone says it's A, symmetric airfoils only. Okay, fine. Others, okay, A. So we are repeatedly saying, getting the answers as A. So let's see. Any other answers? All right. So now let's look into this question. Okay. So clearly, yeah, this is about thin airfoil theory, right? So if you have studied thin airfoil theory, under the assumptions of thin airfoil theory, uh, the assumption is the prime assumption of thin airfoil theory is that obviously the airfoil is much thinner, right? What do you mean by the airfoil is much thinner? The thickness of the aerofoil is negligible compared to the chord length, right? So if you take an aerofoil, okay, the thickness is negligible compared to the chord length. So that is one as one of the assumptions, one of the few assumptions of thin aerofoil theory. Okay, uh, but thin airfoil theory does not say anything about whether it is applicable to only few category of aerofoils, right? Only assumption is that it has to be thin. Now when it is thin, it could be a symmetric airfoil which is thin, it could be a cambered airfoil which is thin, it could be some other type of airfoil, for example a hinged airfoil. Okay, there is also a category of aerofoil which is hinged at the trailing edge. Okay, the one that we had seen in the previous question where we had flaps, right? So thin aerofoil theory is actually applicable to all these type of aerofoils. Only assumption is that it is going to be thin along with some other assumptions, right? Okay. Now let's look at each of these options. So first option says that it is only applicable for symmetric aerofoil. So what is the lift curve slope for symmetric aerofoil, or the lift equation for symmetric aerofoil as predicted by thin aerofoil theory? It is 2 pi alpha, correct? CL is equal to 2 pi alpha. So from here, what can you say? What is going to be the slope? A naught, that is dCl by d alpha, is going to be 2 pi. Okay. So 2 pi is obviously correct for symmetric airfoil, right? Let's look at cambered airfoil. So what is the lift equation for a cambered airfoil? It is 2 pi into alpha minus alpha L is equal to 0. We have seen this in the previous question, right? So this is the lift equation for the cambered airfoil. So again from here, what do you see the lift curve slope is? What is the lift curve slope, guys? It is again 2 pi, right? Because you know, for any cambered airfoil, once you fix the camber line, once you know the camber line equation, alpha L is equal to 0 is fixed. Okay. So once you fix alpha L is equal to 0, if you take the derivative with respect to that, you're going to get 0. So the derivative will still be equal to 2 pi. So 2 pi is valid for not just symmetric airfoils, also valid for cambered airfoils. And not only for these two, it is a general theory which is applicable to any aerofoil shape. Okay, any aerofoil shape under the assumptions. Okay, any aerofoil under the assumptions of thin aerofoil theory. Okay, you should never forget this word assumptions. I cannot randomly say it is true for any airfoil, right? It is true for any airfoil provided it satisfies or it covers the assumptions imposed by the thin airfoil theory, right? So it is true for any airfoil shape, not just for symmetric, not just for cambered. Okay. Now you see option D, you see there is Joukowsky airfoils. Do you guys know what is a Joukowsky airfoil? So Joukowsky aerofoils are generally obtained by conformal transformation. Okay, so they are obtained geometrically by some sort of transformation in complex planes, right? Which is known as conformal transformation. Okay, conformal transformation. Okay, so basically you have a Z plane. Okay, where you have the uh, so you have two complex planes. Okay, say this is a Z plane. Okay, so this is XY. Okay, and you have another complex plane, say zeta, eta, and we call this as a tau plane. Okay, now say you have a circle in the Z plane, which is centered at origin. Okay, if I apply some sort of transformation to the circle in Z plane, and if I want to project this onto the tau plane, right, the transformation is like tau is equal to z plus c square by z. The c square is some constant which can be appropriately chosen to get different shapes, right? So for one particular orientation, so if I move the center of the circle, I can move the center towards x-axis, along y-axis, along any quadrants, right? When I move the center, I'm going to get an aerofoil in the tau plane. How will I get an aerofoil? It depends on the value of c square. Okay, so I'm going to get an aerofoil. Now these category of aerofoils which are obtained through this technique called as conformal transformation are known as Joukowsky aerofoils. Okay, so these aerofoils have a peculiar characteristics like they are usually cusped near the trailing edge. Okay, they have a cusped trailing edge. They do not have finite angle trailing edge. Okay, so the trailing edge is not a stagnation point over here, right? So it is observed that for such airfoils, in general, lift curve slope is going to be less than 2 pi. Okay, so they do not come under the class of thin airfoils because they are sufficiently thicker, right? They are not thin airfoils. Okay, so this option is not just true. Okay, so for this question, only option C is the correct answer. All right. So I hope whoever are watching the session are following it. If it is clear, please comment, guys. If you have any doubts, you can ask. Shall we move to the next question? All right. Let's go to the next question. Okay. So this question says so this is a 2-mark question. Okay, this is a 2-marker MCQ. So let's read a model airfoil in a wind tunnel that is operating at 50 meters per second, right? So see this 50 meters per second is fairly low speed, right? So it is at, so this aerofoil is kept in a, great. I'm glad that you guys are following. Okay. So 50 meters per second, you can see that it is a fairly low speed, right? So this aerofoil is kept in a low speed wind tunnel. Okay. It develops a minimum pressure coefficient of minus 6.29 at some point on its upper surface. And the local airspeed at that point is dash, right? So let's just try to understand this scenario. So what they have told is you have an aerofoil. Okay, you have an aerofoil. This aerofoil is kept in the wind tunnel, right? So this is the test section of the wind tunnel. So what is the purpose of the test section, guys? The test section will make sure that the flow is uniform, right? So whatever model is mounted in the test section will experience a uniform flow, right? So here the flow is going to be uniform. So this is V infinity, right? Flow is going, and you know the characteristics of the flow over an airfoil. What the flow will do? The flow is going to accelerate on the upper surface, right? The flow will accelerate on the upper surface, and because of which the pressure will, to look at distribution, this is Cp versus X by C. Okay, you will see axis go pressure, and similarly
You are currently the only person in this conference.
pressure. Because of this pressure drop, what happens? Your Cp is going to be negative. What did you hear me, guys? Now is it
I think your screen got off. Can you share back and start? And please be little quicker because we have another session at 9:30. Okay?
okay, sir? Yeah, yeah,
Please share it again and start.
yes, yes. Yeah. Now can you see the screen?
We go ahead.
Yeah. Okay. So the pressure coefficient Cp is defined as P minus P infinity by Q infinity, right? Where this Q infinity is the dynamic pressure, right? So you can also write this as P minus P infinity by half rho V infinity square. Okay. So let's take 2 points. Okay. The first point is say anywhere on this free stream, and the second point is on the aerofoil where you observe the minimum pressure condition. Okay, or rather we can call this as yeah, we can call this as infinity, and this is point 1. Okay, so infinity is the free stream and 1 is the point on the airfoil where we have the minimum pressure condition. Okay, all right. So now you know the flow is incompressible, right? 50 meters per second is fairly low speed, so the flow is incompressible. Also the flow is steady, so we can apply what, guys? We can apply the Bernoulli equation, right, across these 2 points. So if you apply the Bernoulli equation, what we will get? P infinity plus half rho infinity V infinity square is equal to P1 plus half rho 1 V1 square. Correct? So from here, what is P1 minus P infinity? That is half rho P1 minus infinity is rho, right? So if I want to find Cp at 1, it is going to be P1 minus P infinity by half rho infinity V infinity square, right? Now this is incompressible flow. So obviously our rho infinity is going to be equal to rho 1 is going to be equal to rho, right? The density is going to be constant in an incompressible flow. So if you substitute this in the numerator of Cp, okay, so what will you get? Cp1 is going to be half rho V infinity square minus V1 square by half rho V infinity square, right? So half rho gets cancelled. What you get is 1 minus V1 by V infinity the whole square. Now you might be familiar with this expression of Cp. It is valid only for a incompressible flow. Okay, don't apply this where a flow is compressible. Okay, this is valid only for an incompressible flow. Okay, so now let's substitute the values. What they have given you, Cp1 is minus 6.25, right, is equal to 1 minus V1. So V1 is the local airspeed at the point 1 is what we need to find. Okay, and V infinity is given to you as 50, right? So you can solve this equation, solve for V1, and you will obtain V1 as 135 meters per second. Okay, so if you see the options, option C is the correct answer. I hope this is clear to you all. Okay, let's move on to the next question. All right, so you can see the next. Consider an ideal city room shown in the figure below, right? So this is the duct. Now what does the question say? Let the cross-sectional areas at section 1 and 2 be A1 and A2 respectively. The velocity measured at section 1 using a pitot static probe is V1. Okay. Then the static pressure drop P2 minus P1 is dash, right? So when you look at this question and you look at the options, you see that the options are in terms of area, velocity, density. So, and you know, this is a question of low speed aerodynamics, right? This is an incompressible low speed aerodynamics. So immediately what should click your mind? That you have to apply the continuity and the Bernoulli equation, right? So let's go back to this question, right? This is the duct that you have. Let's define a control volume, okay? Control volume over this duct. So say this is a control volume, okay? A, B, C, D is the control volume. So you have flow, inflow, this is outflow, right? So here you have the density as rho, area is A1, velocity is V1, okay? And similarly, here the density is rho because it is incompressible, area is A2, velocity is going to be V2, okay? So now let's first apply the continuity equation across AB and CD, right? So AB is the inlet, CD is the outlet. So you apply the continuity equation. So what do you get? Rho into A1 V1 is equal to rho 2 A2 V2, right? Rho 1 and rho 2, right? So from here V2 by V1 can be written as A1 by, right, equation 1. And why? Because the flow is incompressible, right? Or even if you not a streamline through the duct, Bernoulli equation look like P1 plus half rho V1 square is equal to P2 plus half rho square, right? You can consider they are at the same height. So the to derive an expression P2 minus P1. I'm not able now. Yeah, guys, am I audible now? So you can take V1 square outside. So half rho V1 square into 1 minus V2 by V1 the whole square, right? Now you can substitute V2 by V1 from this equation 1. And what do you obtain? Half rho V1 square into 1 minus A1 by A2 the whole square, right? So this is the expression for the pressure drop across the duct. Okay, so you can just see the options. Option B is the correct answer. Okay, so I hope this is clear to you, and let's move on to the next question. So the next question says that you have two vortices, right? Two vortices of same strength and sign. So both are rotating in anti-clockwise direction, are placed at a distance d apart, right? So this is not 4, this is d, right? They are placed at a distance d apart, as shown below. Assume that the vortices are free to move and the fluid is ideal. Okay, the fluid is ideal. So let's see what is the question. What are the options, right? So the options say that vortices 1 and 2 spiral inwards with an initial angular speed to finally merge with one another, or they move perpetually, revolve about the midpoint with a radius of revolution d by 2 and such an angular speed. So basically the options are asking you whether these vortices will move in a circular fashion, or whether these vortices will move in a spiral fashion and they will merge at the center. So what is going to happen over here? So this is one of the tricky question, but it's not really a difficult one. Okay, so let's look at this case. What will happen? So you have two vortices. Okay, vortices, vortex 1, vortex 1 and vortex 2. They are separated by distance d, right? And both are moving in anti-clockwise direction, right? Both are moving in anti-clockwise direction. Okay, so this is also gamma, this is also gamma, right? So you know when you have a vortex, okay, when you have a vortex of strength gamma and you have a point, say this point is P, okay, and say this point is at a distance r from the vortex. What is the velocity induced at this point due to the vortex? It is going to be gamma by 2 pi r, right? This is what we obtain from the potential flow theory, right? So let's use the same concept over here. So you see that vortex 2 is going to induce some velocity at 1 because it is at some perpendicular distance. Similarly, vortex 1 is going to induce some velocity at 2 because it is at some perpendicular distance, right? So let's see what are those velocities. So velocity induced by 2 on 1, okay, which is nothing but V21 is going to be what, guys? It's going to be gamma by 2 pi d. Okay. Similarly, velocity induced by 1 on 2. So vortex 1 is also going to induce some velocity on 2. That is going to be V12, which is again going to be gamma by 2 pi d, because the perpendicular distance is same in both the cases, right? Now what is going to happen? The direction of velocities are going to be different, right? The one is going to induce a velocity in the, you can see one is going to induce a velocity in this direction on 2, whereas 2 is going to induce a velocity in downward direction on 1. Because the directions are completely opposite, right? And you know, these velocities are all tangential velocities, right? The velocity induced by a vortex is a tangential velocity. So what is going to happen here? They are going to move in a circular fashion, okay? Because these are tangential velocities in opposite directions, they will move in a circular way, okay? So basically they'll form a circle like this with center, okay, with the center at the midpoint of this line, and d by 2 will be the radius, okay? So at any 2 points, you see the distance between both the vortices are going to be the same, right? So they are going to move in a circle, okay? Now what they have asked you, they have also asked you to find the angular velocity, right? You also have to find angular velocity omega. How will you find angular velocity? We know v is equal to r omega from rotation, right? V is equal to r omega. Now this v is a tangential velocity that we know it is gamma by 2 pi d. What is r here? Because it moves in a circular fashion, the r is going to be d by 2, right? D by 2 times omega. So from here, what you get omega is gamma by pi d square. So this is the angular velocity, and the vortices are going to move in a circular fashion. So let's go back to the options. You see that option D is the one that correctly says what we have explained, right? They perpetually revolve about the midpoint P with radius of revolution d by 2 and angular speed gamma by pi d square. Okay, I hope this is clear to you all, right? Okay, now just one thing in this question, if instead of ideal, if I say the fluid is viscous, what should have been your answer? Can you all comment? Instead of ideal, if the fluid was viscous, okay, what should have been your answer? Will your answer be D alone, D, or will it change? Okay, so I leave this for you guys to think. Okay, please think about this, and you can comment the answer in the chat box. Okay, or we'll take this up for the next class, right? Right now, let's go to the next question. Okay, so this question is from boundary layer. Okay, it is again a 2-marker question. It's from boundary layer. It's a very easy question. So let's read what this question says. The laminar boundary layer over a large flat plate held parallel to the flow is 7.2 mm thick. So this is the boundary layer thickness. Delta is equal to 7.2 mm. And where is this thickness found? It is found at a point 0.3 mm, 33 mm downstream of the leading edge. If the free stream is increased by 50%, then the new boundary layer thickness at this location will be approximately dash, right? So basically they're asking to layer thickness and the free stream, right? So how do we relate? Let's go back to boundary layer. So you have a flat plate. Okay? You have a flat plate kept in a uniform flow of V infinity. You know there is going to be a boundary layer that will grow on the flat plate, right? Because of the growth of boundary layer, what will happen? What is a boundary layer? It is a thin layer adjacent to the surface of the flat plate where the velocity is going to be less than the free stream velocity, right? So you are going to have a velocity profile, right? So basically it's going to be a parabolic profile in a flat plate. Okay, so because of the edge of the boundary layer, you are going to have boundary layer thickness along the length of the flat plate. So you are going to have delta of x varying along x. Now, how does this vary? So this solution to the flat plate boundary layer problem was given by Blasius. Okay, so we have Blasius solution. Okay, what does Blasius solution say? The boundary layer thickness delta, okay, delta by x is inversely proportional to the square root of Reynolds number. This is directly from the Blasius relation. So Blasius had obtained a series of analytical solutions for flat plate boundary layer problem, and you see that the boundary layer thickness is related to x and it is related to the Reynolds number. Let's now simplify this a little bit. So you can say delta is now proportional to x by root of. So how do you define Reynolds number? Reynolds number is V infinity x by nu. What is this nu? Nu is the kinematic viscosity, right? Nu is equal to mu by rho. Okay, it is a kinematic viscosity. So I can say delta is now proportional to root of nu x by V infinity, right? So I can, so when you are comparing both the cases, nu is constant and x is constant, right? You are comparing the boundary layer thickness at the same x location. So I can say delta is inversely proportional to square root of free stream velocity, right? So from here I can say delta 1 by delta 2 is going to be square root of V infinity 2 by V infinity 1, right? And they have given you that V infinity 2 is 50% more than V infinity 1. What does that mean? V infinity 2 is equal to V infinity 1 plus V infinity 1 by 2. So this is 3 times V infinity 1 by 2. So if you substitute over here, you will get root of 3 by 2. Okay, so which means delta 2 is equal to root of 2 by 3 times delta 1. Delta 1 is given to you as 7.2 mm. Substitute over here root of 2 by 3 into 7.2 and you will obtain the answer as 5.87 mm. Okay, so you can see that option C is 5.9 mm, which is the correct answer. So this is a fairly simple problem. If you know boundary layer and the Blasius solution, you can easily tackle this, right? So I hope this is clear to you. This was the last question. So I hope the session was really useful to you guys. You can contact us here, and thank you. If you have any doubts, please please ask in the comment section. I'll be happy to answer. Any doubts, guys? All right. So if there are no doubts, we can wind this up. Thank you so much.